Assalamu alaikum. In today's lecture, we are going to calculate the capacitance of a three-phase line. So there are two orientation in which we can have the three phases of the overhead transmission line. The first one is the equilateral spacing, and the second one is the unequilateral spacing or unsymmetrical spacing. In equilateral spacing, we have equal distances between the conductors. For example, in this case we have A, B and C conductors, and the distances between the conductors is equal to D. We have to find the line to neutral capacitance, and the formula for the line to neutral capacitance is charge over that conductor divided by the voltage between that particular conductor and the neutral point. So this is the scenario that we will be discussing and using to formulate the formula. So what we are assuming is that there is a point in between the two conductors which is actually the neutral point. So we have the capacitances that is divided into two parts, and each capacitance, for example this Cn is actually the line to neutral capacitance. This Cn is the capacitance between this conductor and this neutral point. So in order to calculate the line to neutral capacitance, we should divide the charge over a particular conductor divided by the voltage of that conductor till neutral. We know the formula for the potential difference. The formula is 1 over 2 pi k charge of a conductor L and D over R. So this is the formula that we used for the single phase line when we are having the charges Q1 and Q2, and the one was the forward conductor, the other was the reverse or return conductor. But in that case we considered that the charges were equal, right? So therefore the formula was in the reduced form. But if the charges are different, for example in this case QA and QB, then the formula will be this one. Just to revise the formula, that how we will write this formula for the voltage between conductors A and B. The first abbreviation small a, that will be the high potential point or the high potential conductor, and the second one is the low potential conductor. And in the logarithmic term we have the low potential point distance from the other conductor and the high potential point distance. So in this case, if we have to find the voltage VAB due to charge QA, the assumptions remain same like in the last lecture when we were calculating the line to line capacitance. So we were starting from the charges, and when we were considering one charge over a conductor, the other charge was considered to be 0. So in this case the condition remains same. If we have to calculate VAB due to charge QA, then the logarithmic term will have the low potential point distance in the numerator and high potential point distance in the denominator, and the high potential point is A and the low potential point is B. So from the figure you will see this is your point A and this is your point B. The high potential point has a distance R and the low potential point has a distance D. So low potential point has a distance D and the high potential point is R. Now for the second part, again we will assume that the charge over the conductor A is equal to 0. So we only have QB charge. From this VAB we can say that the low potential point is B. So in this case, if the low potential point is B, then the distance of low potential point is R, and the distance from the high potential point is capital D, because from VAB we know that the high potential point is A and the low potential point is B. So this was the case when we have two conductors, but now we have three conductors A, B and C and three phase transmission line. So in order to add the third term in this equation, we have VAB, A is the high potential point, B is the low potential point, and now for QC, A and B both has the distances D from the conductor number C. So in numerator and in denominator we have D in both the cases, because the high potential point has a distance D from the conductor C and the low potential point also have the distance D from the conductor C. So this is the voltage value when we have all the conductors considered, VAB value. Now we will have to find VAC. Once I will find the VAC, then I will tell you that why we are calculating VAB and VAC. So VAC value is actually the same procedure we have to adopt in order to calculate the VAC value that we have used for VAB value. So 1 over 2 pi k QA, high potential point, I will write it here, high potential point is A and the low potential point is C. This is your high potential point, this is your low potential point. So now charge, due to charge QA, we are here. So high potential point, it should be in denominator and low potential point in the numerator. So due to QA, if I am considering QA, the high potential point is R, which is in the denominator, and the low potential point is at distance D. Now for QB, we are here. Now high potential point is at A and the low potential point is at C. So in both the cases we have the distance D. So in natural logarithmic term we will have D in the numerator as well as D in the denominator. Now for QC, again the low potential point will be in the numerator. So for QC the low potential point is R, and for the high potential point the value is D. So this is the value of VAC, right? In the start of the lecture I told you that we have to calculate VAN so that we can calculate CAN. This is line to neutral capacitance, this is a line to neutral voltage. We know that VAN, VBN, VCN, they are 120 degree apart from each. Now for the line to line voltages we have VAB, VBC and VCA, which are also 120 degree apart. Now we have to find this line to neutral voltage, and this line to neutral voltage can be written as the summation of two of the line to line voltages. For VAN we have the summation of VAB and VAC, because this is VAB and this is VCA, so this will be your VAC. So this is your VAC. So this is just the extension of VAN. So there should be a multiplying factor with VAN that will be equal to, for example, I am saying this is X VAN. We don't know what is the numerical value here, right? So to calculate the VAN, we will add VAB and VAC, which are the line to line voltages, and that will give you the value of VAN. And we have to find this magnitude value, this X, what is the numerical value here. And from the figure we know that this angle is 30 degree, which is anti-clockwise, and this angle is minus 30 degree, which is clockwise. So the angle measured in clockwise direction, that is negative, and the one that is measured in negative direction or the anti-clockwise direction is the positive value. So we can say that VAB is actually equal to under root 3 VAN angle 30 degree. Similarly, VAC is equal to minus VCA is equal to under root 3 VAN angle minus 30 degree. So line to line voltage has greater magnitude in comparison to the line to neutral voltage, and the value is under root 3, with which you have to multiply it in order to get the magnitude of line to line voltage. Now VAB is equal to under root 3 VAN angle 30 degree. That is actually equal to under root 3 VAN 0.86 plus 0.5 J. This is VAB, and for VAC again is equal to minus VCA under root 3 VAN angle minus 30 degree. So this sign will be replaced by minus under root 3 VAN 866 minus 0.5 J. And when you will add these two values, you will get VAB plus VAC equal to 3 VAN. So this X is actually equal to 3. So when you will add these two line to line voltages, the value will be equal to 3 into line to neutral voltage VAN. VAB plus VAC is equal to 1 over 2 pi k. We are just adding these two values. So there are two terms for QA ln d over r, and single term for QB and single term for QC. And this value QB will be equal to 0 because d over d is equal to 1, ln 1 is equal to 0. Similarly, for the last slide, this value will be equal to 0. So we have only 4 terms in VAB plus VAC term, and this VAB plus VAC is equal to 3VA, right? And as it is a balanced system, we know that in balanced system the summation of currents, the summation of voltages, that is actually equal to 0. So that's why we have the summation of charges also equal to 0. So to replace this QB and QB plus QC with QA, we will have this equation, and QB plus QC is equal to minus QA, right? So I will write it here. The VAB plus VAC term is equal to 1 over 2 pi k 2 QA ln d over r plus QA ln r over d, and further simplifying will give you VAB plus VAC is equal to 1 over 2 pi k 3 QA ln d over r, and this is equal to 3 VA. VA or VAN both are the same value. Now VAN will be equal to Q over 2 pi k ln d over r, because this 3 will cancel out with this one. Now in the start of the lecture I have written the formula for the line to neutral capacitance, that is equal to QA over VAN, QA over QA over 2 pi k into ln d over r. So this QA will cancel out, and the line to neutral capacitance for a 3-phase line will be equal to 2 pi k over ln d over r farad per meter, and this value is line to neutral capacitance, right? Now if you have to find the charging current, that is the current associated with the capacitance, that will be equal to I charging V phase, which is VAN or VBN or VCN divided by XC, and this XC is equal to 1 over 2 pi FC, and this C value is actually CN or CAN. You can use either of these notations. So this was the formula calculation for the equilaterally spaced 3-phase overhead transmission line. Thank you.